So good afternoon one and all. Your course name System Design and Control. In that you are going to discuss about the stability of a control system. So what is stability? The term stability refers to the stable working of a control system. Every working system is designed to be stable. In a stable system, the response or the output is predictable in nature, and at the same time it is a finite and stable for a given input. So what is a bipole stability? That is a bounded input, bounded output stability. A linear system is said to be a bounded input, a bounded output stability. If its output is bounded, that is a finite for an any bounded input. Next, stability, that is limitedly stable for a bounded input signal. If the output has a constant amplitude oscillation, then the system is said to be limitedly stable. Next, we discuss about the absolutely stable system. If a system is stable for all variant of its parameters, then the system is called absolutely stable system. Next, conditionally stable system. If a system output is stable for a limited range of variance for its parameter, then the system is called as a conditionally stable system. So these are all the different stability. That is, the first one is a limitedly stable, absolutely stable, and a conditionally stable. So each and every has a mode. That is, limitedly in the sense you have a limited, and absolutely can perfect for that is stable for its particular variance, and conditionally stable, and it takes the limited range of variance. Next, location of poles on S-plane for stability. So for closed loop transfer functions, that is m of s, can be expressed as a ratios of two polynomials in S domain. The denominator polynomial of a closed loop transfer function is called a characteristics equation. The roots of a characteristics equation are called poles of a closed loop transfer function. For a bounded input, bounded output stability, the integral of impulse response should be finite, which implies that the impulse response should be finite as t tends to infinity. The impulse response is the inverse Laplace transform of the transfer functions. This requirement for a stability can be linked to the location of the roots of characteristic equations in the S-plane. Next, the closed loop transfer function m of s can be expressed as a ratio of two polynomials in S domain as shown in equation. M of s, that is equal to b naught s power of m plus b1 s power of m minus 1 up to bm minus 1 s plus bm divided by a naught s power of n plus a1 s power of n minus 1 up to of a of n. So this can be expressed as s plus z1 into s plus z2 into s plus z3 up to z plus of z suffix m divided by s plus of p1, s plus of p2 up to s plus of p by m. The roots of numerator polynomial is z1, z2 and up to z are called zeros. The roots of the denominator polynomial, that is a p1, p2, pn are poles. The denominator polynomial is the characteristic equation, and so the poles are roots of the characteristic equation. So the following conclusions are drawn based upon the locations of the roots of the characteristic equation. So if all the roots of the characteristic equations has a negative real parts, that is the roots are lying on left half of your S-plane, then the impulse response is bounded, that is it decreases to 0 as t tends to infinity. Hence integration of 0 to infinity m of t dt is a finite, and the system is bounded input and bounded output stable. If any roots of the characteristic equation has a positive real part, that is lying on right half of your S-plane, then the impulse response is unbounded. It means that it increases as t tends to infinity, as t tends to infinity. Hence, the integration of 0 to infinity m of t into dt is infinite, so system is unstable. So third one is, if the characteristic equation has a repeated roots on imaginary axis, then the response is unbounded, that is it increases to infinity as t tends to infinity. Hence, integration of 0 to infinity m of t into dt is infinite, and so the system is unstable. Fourth one, if one or more non-repeated roots of the characteristic equations are lying on the imaginary axis, then the impulse response is bounded, but it is infinite, so the system is unstable. Your fifth case is, if the characteristic equation has a single root at the origin, then the impulse response is bounded, that is it has a constant amplitude, but integration of a 0 to infinity m of t into dt is infinite, so the system is unstable. Here, sixth one. If the characteristic equation has a repeated roots at the origin, then the impulse response is unbounded. I mean that here it linearly increases to infinity as t tends to infinity. So the system is unstable. Here, seventh case. In a system with one or more non-repeated roots on imaginary axis or on a single root at origin, then the system is bounded or bounded inputs except the inputs having the poles matching the system poles. The cases may be treated as acceptable or non-acceptable. Hence, within the system has a non-repeated poles on imaginary axis or a single pole of origin, it is referred as limitedly or marginally stable system. So next, in overall summary, the following 3 points can be regarded decide the stability of the system based upon the locations of the roots of the characteristic equation. Your first case, if all the roots has a negative real parts, then the system is stable. I mean that here if all has a negative real parts, that is the roots of the characteristics equation has a negative real parts, then the system is stable. If any roots of the characteristics equation has a positive real parts, or if there are repeated roots on imaginary axis, then the system is unstable. If the condition is one is satisfied except for the presence of one or more non-repeated roots on imaginary axis, then the system is limitedly or marginally stable. Here, based upon the coefficients of the characteristics polynomial, in addition to that, we have to decide that if all the coefficients are positive and if no coefficient is 0, then all the roots are on the left half of your S-plane. If a coefficient is equal to 0, then the sum of roots may be exist on imaginary axis or on right half of a S-plane. If any coefficients is negative, then at least one root in the right half of a S-plane. So based upon this, we can say that how the roots, that is the poles on a S-plane, can decide the stability of the system. Here I mean that a 0 coefficient indicates the presence of complex roots on the imaginary axis and are one or more roots in the right half of a S-plane. So here it indicates that the roots with the negative real part, which is always true. Here I mean that roots can exist with a negative real part, which is always true if all coefficients are positive. In another case, if all the coefficients are positive, it's not always true that the roots with the negative real part. I mean that it is of a vice versa case. So we have to look into this also. So based upon that, we can decide the location, that is based upon the roots located on either it may be in right half of a S-plane or left half of a S-plane or imaginary axis. We can decide the stability of your systems. So thank you one and all for watching this.